All right. So quick outline of what we're going to be doing today. So we're going to provide a very basic overview of STATA and essentially provide some resources that you can refer to, some basic first steps for how to get started, some examples for how to clean your data. We're going to go into baseline characteristics, regression basics, and finish off with some final tips. And we're going to see how far we can get today. But we may have another session in this series if we don't finish everything today. So starting with the introduction and resources. So big picture overview. Essentially what we're trying to do is at this point, you've come up with a clinical research question. You've come up with a question, ideally with a mentor who can guide you in the right direction to make sure your question is clinically relevant. But then also technically and logistically feasible. And so that means that with the data that you either already have or that you're able to gather, you can actually answer the question that you're interested in answering. And so the next thing you'll have to do is you'll have to look at data sources. So what data are you going to use to answer this research question? Is it going to be a large national data set like the way UNOS is with transplant data? Is it going to be institutional? So data that you'll have to collect through your own institution data. A lot of times that's through chart review or through institutional STS data. And you have to evaluate whether any additional data collection on top of what you already have will be necessary. So if it's a completely novel question and no existing databases can answer it, then you might have to collect your own data from scratch, essentially. If it's, for example, transplant-related question, you can always use your institutional transplant UNOS data and then supplement it with additional UNOS or additional institutional chart review data. And so you'll have to figure that out. And thinking about workflow. So essentially, once you have your data set, once you figure out what data you're going to use, and for today's example, we're going to use essentially a modified version of UNOS data. Essentially, what you're going to do is you're going to take the full data set, you're going to apply study inclusion and exclusion criteria. So this can be time periods. You can say, I want to look at the years 2020 through 2024. This can be, for example, different patient populations. So excluding all patients under the age 18, for example. Once you apply your inclusion exclusion criteria, you're going to have your project data set. So this is essentially the data that you're working with for your specific project. From there, you're going to clean your variables, restructure your data set. You're going to merge in new data if needed. So sometimes you're going to have lots of data sets. So for example, if you have an Excel sheet with all your patients of interest and you have their ages and their genders and their ethnicities on one data set, but then on a different Excel file, you have all of their transplant related information. So their surgery date, their donor date, or their donor information, et cetera. And you want to merge those into one data set. That's what we mean by merging data. So you want to make sure all the data that you need is all together in one data set. That might involve some more complex restructuring that we're not going to get into too much today, but all that would go under sort of cleaning your data set. And so once you do that, you're going to have a final clean data set. And then with that, then you'll perform your statistical analyses. And so it's really important that you go through sort of each of these steps and make sure that in the end, before you start your analysis, you have a very clean data set that's easy to work with, reproducible, and if needed, you can give to other members on your team to continue if, for example, you can't continue with the project. So just an overview of what the STATA window is going to look like. So I'm going to pull up STATA on my other desktop in just a moment, but here's a screenshot of what it might look like. So right here in the middle, you have your results window, and that's essentially any output that you have is going to pop up in the results window. Right below that is your command window. So that's where you can type your commands, type your lines of code, and when you hit enter, it's going to run, and whatever output you're going to get is going to pop up in the results window. On the right side, on the top, you have the variables window, and so that has a list of all variables in your data set, and so variables are columns. So for example, age, gender, ethnicity, et cetera, those are all variables. And then bottom right is your properties window. So that'll tell you properties about your entire data set. So it'll tell you how many total variables you have, how many observations you have, the size of your data set, that sorts of information. And then on the left, you have your history window, and that essentially keeps a log of all the commands that you run. And then the next really important thing to know is what a STATA do file is. So a do file essentially is a text file that contains all of your STATA commands. And so this allows you to save your work in a very reproducible manner. So while you can in the command window just go and type individual commands and hit enter each time, a more reproducible way of coding is to actually write all of your code all at once and then run it from your do file. And that way you can save your do file. You know exactly what you did to your code. The next time you want to reload your data, all you have to do is open up your do file and run everything again. And then you'll be at exactly the same point you were last time. And so if you're doing full projects with Stata, really all the data manipulation and analysis should always be done using a do file. And I'll give you some more examples of that when we go into our example coding. Okay, so moving on to first steps. So now I'm going to ask Emily, you can stop sharing your screen, and then I'm actually going to share my safe desktop. Okay. Can everyone see this? Safe desktop? Okay, perfect. So essentially, Safe Desktop is our Hopkins version of where we have all our data in a safe drive, essentially. And so this is where we have access to data, and this is where I do all my data analyses. So essentially, I'm just going to go ahead and open Stata. We're using Stata version 18 here. And this is all live. So this is exactly what we see right when we open up Stata. And this is the window that we saw earlier. So again, your command window's down here, your results here. And then if we click this button here, so this is what's going to open a new do file. And so we can go ahead and click that. And the way I like to set up my window is I like to put my do file on the left side and then the actual Stata window on the right side. And so here we can, here's essentially with this do file on the left side, this is where we're essentially going to type all of our commands. And then when we run it, it's going to run here on the right side. And so just sort of housekeeping for how I like to set things up. I always start with some basic information, like at the top, put my name down just so I know it's mine. Project, for example, Stats 101, Intro to Stata. I always like to have a date down. And so that way, if I ever go back and open up my old do file, I'll know when the analysis was done. And that way I can keep everything organized. And so this is what I like to do in every single do file that I make, is always include these items here at the top. We can also go ahead and save this do file just in case. So we can save it as, let's just save it as stats intro to Stata. Okay. All right. So the first command you always want to run is clear all. And essentially that tells Stata to clear everything in its history. So if you have the Stata window open, you've already been working on Stata for another project, and you want to switch over to this project, you should clear all. And the way you actually run a command in Stata, so once you type it here in your do file, you highlight it and then Command D if you're on Mac or Control D if you're on a Windows. So everything that you highlight and you hit, every time you hit Command D, it's going to run here and you'll see that it's run. So I just ran the clear all again. And so the next thing we're going to do is we're going to import the data set. So the other thing that I should explain is, so when you start a Stata line with a star, essentially you're commenting out that line. And so whatever is in a star is not actually going to run. So that's why these first three lines are all starred. And so for this next one, I'm going to start again. I'm going to say importing data set. And this is just a comment to myself about what this next group of lines is going to be. So importing data set, and how we're going to import it is we're going to say use, and then we're going to find the data set. So this is where I have the fake data for today is right here. So I'm going to go to my folder. I'm going to copy over the actual folder name and then put in the name of the data set. So fake data .dta. And then if you run this line, essentially what you'll see is that it's pulled up all the data in your STATA window. And so how you can tell is if you look here on the right, you see the list of variables. And so we can see all the variables that I've included in this data set. And you can also see in the properties window, you can see stuff about your data. So you can actually see in this data set, remember this is similar to UNOS, but it's a fake data set just with variables that we're interested in today and data that we've essentially recreated. So we're not actually using any patient identifiers here. What you can see is we have 10 variables. And so we see variable over here on the right in the properties window, we see 10 variables right in here. And then we also see that there are 217,648 observations. And so that essentially means we have 240 rows of code or of patient information, each row being one patient basically. And so we can see that with a data set this large, this is why we can't really use Excel for data analysis, because Excel can't really handle 200,000 plus rows of data very easily. And so that's why we're going to still use, that's why we're using STATA instead. And then we also see information on the size of the data set and memory as well, and the file name. And so starting with this window, how I was able to actually see the data is with a command called browse. And so that allows you to pull up the data, and this allows you to actually see what the data is without actually being able to edit it. And so, for example, if I go here and I click delete, I'm not actually deleting any data. And so this is a very safe way of viewing your data. There are ways of viewing it in edit mode. So for example, if you go up here and you hit edit, or you just run the command edit, you can actually manipulate your data right here, for example. And so it'll allow you to change your actual values. But I don't like to do this. So I don't like to actually manipulate manually any of my data, because that's not reproducible. And so instead, what we're going to do is we're going to only look at our data using browse mode, which we look at with either browse or with shorthand. We can just type BR. We see the data. We're not able to manipulate it, but that's okay, because we're going to manipulate it with code. And so this is just giving a quick overview on what the data actually is. So gender here, male, female, that's pretty self-explanatory. Intubated 72 hours. So this is going to be one of our outcome variables that we're going to look at. Essentially, we're just looking at whether or not patients were intubated at 72 hours post-transplant. Patient stat here is whether or not the patient was alive, dead, retransplanted at time of last follow-up, and I'll go into that a little bit later. For organ type, as I mentioned earlier, this data set was heart transplants, lung transplants, and then heart-lung, which is indicated as HL. For candidate code, so this is a completely made-up variable that we just assigned code names or code numbers to each candidate. It's not actually a variable in UNOS. They have a different identifier variable. Age, here is the age of all the candidates. And again, all these numbers are made up, and that's why it might look a little off. Like we don't actually have this many 80-year-olds necessarily getting transplanted. And then LOS is length of stay. Again, we manipulated all this data, so it's not real data. But it's post-transplant length of stay. So this patient, for example, stayed post-transplant 19 days in the hospital. And then we have transplant date, again, fake transplant dates, but this patient, for example, in this fake data set was transplanted April 11th, 2017. E time I'll go into later, and then ethnicity, FCAT is ethnicity. So these are different categories of ethnicity that I'm going to go into later. And aside from candidate code, all these other variables are actual variable names that we would see in UNOS. So for anybody who's doing a UNOS project, these are actual variable names that you can use. So going back to our code, the next thing we want to do is called change directory. And so we're going to do it by with the command CD, which stands for change directory. And this essentially tells data where I want to store any outputs, any files, any new saved data sets for this project. And so I like to create one folder per project and then use this command to make sure that everything from this code coding session goes into that folder. And so for the purposes of this, I'm going to put it into the folder called Stats 101 for this series, and then we're going to run that. And essentially it tells Stata that we're changing the directory to this folder here. All right, so moving on to the next part of the code. So after importing the data set and changing the directory, usually I go into inclusion exclusion criteria. So this is the part of the project that I mentioned earlier, where we're really taking the full data set and we're whittling it down to what we're actually interested in for this project. And so you're going to come up with the inclusion exclusion criteria before you get started. For the purposes of this analysis, we're just going to give some examples, and I'm going to use this to also demonstrate some code. So the first exclusion criteria I'm going to say is drop if age is less than 18. So essentially what we're telling Stata here is we're telling Stata to drop any patient, so any row where each row is one patient's information. So for example, patient one's information is row one. We're telling Stata to drop any row if age for that patient is less than 18. So this is our way of excluding any pediatric patients. So we can run that here in this data set. That essentially dropped 8,850 observations from, we started around 200 and something thousand. So we dropped 8,000, we're now at 208,000. So from there, the next thing I'm going to do is I'm going to drop if organ is heart or organ is heart lung. And so for this project, I'm just going to keep lung transplants. And so a few things about this line of code that I just did. So dropping, again, same code, same command as earlier. We're dropping if the organ for any patient, so the transplanted organ they received, is equal to a heart. So we designate that with two equal signs. So equal heart, or with the or being designated with this vertical line, organ equals heart lung. And then in this line of code, I commented out. So remember, comments are anything that's in green. So anything that starts with the star. But if you want to comment out the rest of a line, for example, then you can use these two forward slashes, and then everything after the two forward slashes is commented out. So this is just me dropping any heart or heart lung transplants and just keeping any lung transplants, and then also including a comment to myself that this is what I'm doing, is just keeping lung transplants. And so if we run this in this example, we dropped 86,000 observations. So this was 86,000 cases in which somebody got a heart or a heart lung, and we're not interested in that for the purposes of this of this example. So the next thing I'm going to do is I'm going to drop if transplant date equals period. And so what this line is saying is essentially I'm going to drop, so same command as earlier, drop if anybody has a transplant date equal to a period. And what does a period mean? A period in Stata means missing data. So anything that's missing is coded with a period. And so essentially what we're saying is we're dropping anybody with a missing transplant date. And so what does that actually mean for our data? So if we look at our data again, we look at the transplant date here, we see that there's a lot of missingness. And so like this patient here, patient number 3, has a transplant date January 22nd, 2000. And then patients 4 through 23 are all missing. And so essentially in UNOS data, this is telling us that patients 4 through 23 were candidates, but they never actually received a transplant. So they were removed from the list for whatever reason, or they died prior to getting a transplant. So only people who got a transplant will have a transplant date. And so if, for example, I'm trying to only look at lung transplant recipients, so those who got lung transplants, what I'm going to do is I'm going to drop if the transplant date is missing. And we can see that 71,000 observations were deleted, and we're left with 50,000 adult lung transplant recipients at this point. The next one I'm going to do is I'm going to drop if transplant date is less than, we're going to say month, day, year, January 1st, 2000. So here I'm telling Stata to drop any transplants that occurred before January 1st, 2000. So MDY, this is the format for January 1st, 2000. going to drop that. We see 7,000 were deleted. And then I'm also going to say drop for transplant date greater than MDY 09/30/2023, for example. And this drops anybody who is transplanted after September 30th, 2023. So I did just want to explain why we might want to drop patients after a certain, so why we're dropping patients before a certain date. So before 2000, that's a little bit easier to explain. Essentially, we want our study to start in the year 2000 for whatever reason. So we drop everybody before 2000. If it's something like we're more interested in contemporary outcomes, we can limit it even further. So we can drop anyone before the last 5 years, for example. So before 2020. And so it really depends on what you're trying to look at. For why you would want to drop patients for after a certain date. So this really depends on your data set. So the data set that we created this fake data based on really only contains data through December of the end of 2023, basically. So we use a data cut that goes up until 2023, so December of 2023. And the way UNOS works is that that transplant centers have 3 months to input their data after transplant. And so what we like to do is we always like to cut off the last 3 months of data just to make sure all the data we have is accurate. And it's within that window, you're not using that window of time when transplant centers can still go back and update data. And so that's just something to keep in mind, is you never want to go fully up until the censorship of your data set. Basically, you want to cut it off a little beforehand. And it's key to really know your data set and know how your data is collected in order to know how much time you want to cut off at the end. All right. So now we've applied our inclusion-exclusion criteria. We went from over 200,000 observations, and we're now down to 38,000 observations. And so this is going to be, for the purposes of this example, our project data set. Essentially, we have adult lung transplant recipients transplanted between January 1st, 2000 and September 30th, 2023. And so the next thing we're going to want to do is we're going to want to clean our data set. So cleaning our data, this is probably one of the most time-consuming parts of any project. But if you go through this once and you kind of clean all your UNOS data and you use a similar data set the next time. So if you were to use UNOS this time for one project with one data set, and then you want to use UNOS again for a similar but slightly different question, you can reuse a lot of your code, a lot of your data cleaning code. And so I'm just going to run through some example variables. And so let's start with age. So let's say we want to clean this variable age here. The first thing that I always like to do is I like to take a look at what it actually looks like. So I browse, I look at the data, and I say, okay, these are the ages. So they're whole numbers, which is good. That's what we're expecting. Nobody under the age of 18, which is good. That's what we're expecting with this exclusion criteria. So what we're going to do is we're going to go ahead and start looking at age in more aggregate form. So one command that I always like to run is summarize, and summarize can be shortened to sum. And then if you type in your variable afterwards and you run this, essentially what you're getting is you're getting a summary of this variable age. And so what the summary will show you, it'll show you the mean. So the average age in this fake data set is 60, standard deviation is 15. The range is 18 to 85. And then if you want more details, you can do summarize again, age, comma, D for detail. And then if you run that, you get a little bit more of a summary. So here you still get your mean, your standard deviation, you get your range with your smallest and largest. But if we're actually interested in the median, for example, we can actually see that the 50th percentile is 62. We can get IQR through the 25th percentile and the 75th percentile. We can get some variance, skewness, and kurtosis values as well. And so I always like to take a look at everything, get a baseline of what we're working with here before I start cleaning the variable. And so for this variable, it's actually fairly clean. It's straightforward. It's age. We have age in years. They're written out very well. So maybe all we're going to do is actually give this variable a name. So The variable is age, but if we want to give it a label, we can run this command. So label var for variable, the actual variable that we want to label, so age, and then we can give it a name. So I like to give it like a name like recipient age in years. And this is essentially, if you think about a table one, so your baseline characteristics like Emily showed earlier, what you want that left-hand column to actually say for this variable. And so I like to say something like recipient age in years. So if you run that, essentially, now your age is going to have a label. So if you go to your variable window here, you have your the name of your variable and then the actual label itself. So recipient age in years. And so I'm going to say age is cleaned at this point. So the next thing I want to do, so I always like to label so we can say recipient age. The next variable we want to clean is recipient sex. And in UNotes, it's the variable's gender. We take a look at it and we look at gender, we see that it's M or F for male or female. And instead of summarizing it, because summary is not going to tell you that much because we're not going to have a mean for male and female or a median, for example. So instead for categorical variables, what I like to do is I like to run this command. So tab, which stands for tabulate, and then the variable name. So tab gender. Essentially what we see here is we see the number of females and males in this data set. So we can see that 58% were male and 42% were female. So that'll give you a good overview of what you're dealing with. And so for a variable like this, where it's categorical or it's a binary variable, we can keep it like this, where it's a string variable of either M or F for male or female. But oftentimes when it comes to analyses, it's actually much easier to have it in string or in integer form. And so essentially we want to take the string data and put it in a 1-0 format, where 1 is either male or female and 0 is the other of the male or female. And this makes it much easier in terms of running analyses, actually doing stuff with your code. And so I like to do that for a lot of these categorical variables. And the way I do it is I am going to create a variable. So I'm going to generate a variable with the generate command. So gen for generate. I'm going to give my new variable a name. So I'm going to say recipient male, for example. And then I'm going to say that recipient male as the new variable is going to be 1 if gender is equal to male. And so I can run that. And essentially what we're saying is that we're labeling anybody with gender equal to M as being a male. So recipient or rec male equal to 1. And so what this command actually looks like. So gen means generate. You're going to generate the variable that you want. So the new variable that you're interested in, which is rec male in this case. You're going to set it to equal to 1 when gender equals M. And so here you'll see two kinds of equal signs, and this is really important for Stata. So one equal sign here in the first part of the command essentially means to set equal to something. And so essentially you're telling Stata to set recipient male, the variable, equal to 1 with 1 equal sign. Whereas if you have 2 equal signs, so the double equal signs, essentially you're testing for equality here. So you're telling Stata to test for whether or not gender is equal to male. And if so, then you're going to set recipient male to 1. So that's the syntax for this variable. And the next thing I'm going to do is essentially, if we take a look at what we've done, we can see, so our gender variable is here on the left-hand side, our new male variable is here on the right-hand side. We can see that anytime gender is M, it corresponds to recipient male equaling 1. But what we'll notice is that all the females are missing. And what we want to do is we want to fill in those missings with zeros. So what we're going to do is we're going to run this command, which is replace recipient male equals 0 if gender equals F. So very similar command. This time we're going to use the word replace instead of gen for generate. We're going to replace and we're going to say change this variable to 0. And The reason why we're using replace here is because recipient male already exists as a variable, and so we can't generate another one that says recipient male. We're trying to tell STATA to use the existing variable, set it to equal 0 if gender is equal to F or female. So we run that. We see that some replacements were made. So 16,132 changes were made, which corresponds to how many females we have. We can take a look at the browse window, and we see that every time the gender is F, it corresponds to recipient male equaling 0. And so essentially we clean this variable, but now we want to add some labels to it just so it's not as confusing for the future. And so what I like to do is I like to label the variables. So let's say label variable recipient age. So like we did earlier, or not recipient age, recipient male, like we did earlier, and we can say recipient male. And that way we give it a name so we remember what it means. The other thing I like to do after creating any variable is I always like to check the variable that I created. So remember we tabulated earlier with gender. And when we did that, we saw we had 16,000 females, 22,000 males. And then I like to tab my new variable, recipient male, and just make sure that the numbers align how we expect it to align. So we look at it, we see recipient male and perfect. We see 0, 16,000, so exactly the same as female from earlier, and male being 22,000, again, the same as earlier. And so we know that the variable we created worked essentially. And so that wraps up our cleaning for this variable, recipient sex. The next one I'm going to do is recipient race. And so this is going to be very similar to how we did this, the sex variable. And we're going to take a look at what it is already coded. So here it is FCAT, and we see it's either 1s or 2s or 4s or 5s. Essentially what you're going to have to do to be able to understand what these actually correspond to is you have to go to your data dictionary. And so UNOS with this data will publish a data dictionary. You go there, and through the data dictionary, you'll be able to see what these numbers actually correspond to. So I worked with UNOS data a lot, so I know what these numbers correspond to. If we tabulate and actually look at what we have, we can see that 66%, 67% of all of the recipients in our data set have an FCAT equal to 1, which is white based on the data dictionary. 2 is Black, 4 is Hispanic, 5 through 9 are other kinds of races. 998 is unknown in UNOS, and so we have 9 with unknown races. And so essentially what I'm going to do is I'm going to do something very similar. Is I'm going to essentially recreate this variable. But let's say, for example, for the purposes of our study, we're not interested in whether somebody, we want more broad categories. So instead of having like 10 race categories, let's say, for example, we want just 4 race categories. We can say white, Black, Hispanic, other. And so we're going to group essentially everything that's not white, Black, or Hispanic. We're going to group that into the other category. And so what I have to do is essentially recreate this variable. So what I'm going to do is I'm going to gen recipient race, a new variable called recipient race. I'm going to make it 0 if FCAT equals 1. And I'm going to say this is for white recipients. I'm going to replace recipient race equals 1 if FCAT equals 2. So this is for Black recipients. Replace recipient race equals 2 if FCAT equals 4. So this is for Hispanic. Replace recipient race equals 3 if FCAT equals 5. Or, so remember this is the or sign, FCAT equals 6, or FCAT equals 7, or FCAT equals 9. And so we're gonna, and this is gonna just mean other. So if we run this, essentially we run it, what we want to do is we want to make sure that everything looks right, so we can tab it. So tab recipient race. And what we see is we have 0 for white, which is 25,000, so it corresponds correctly. 1 is black, 6,000 corresponds correctly. 4 is Hispanic, which corresponds correctly up here. And then our last other category is about 3,000, and it's a sum of everything else we had. And note that I didn't do anything with the unknown, so that's going to end up being missing in our data set, which essentially the unknown means missing. And so we see that it's all done correctly, but now we want to label it to make sure that we know what we're talking about, especially when there are different categories and we don't know what these numbers actually correspond to. And so this is how I'm going to label it. So I'm going to use the label define command. So I'm defining a label, and the label is going to be called race underscore label. And what it's going to mean, the code for the label is 0 is going to mean white, like in this first line. 1 is going to be black. 2 is Hispanic. 3 is other. So essentially we're defining a label called race label, and this is the code for it. And it corresponds to how we coded our variable. And next we're going to tell STATA that we want to apply this new race label to this new recipient race variable that we generated. So how we're going to do that is we're going to say label the values of recipient race with the race label essentially. So if we run this code, and then we now again have recipient race, or a new variable that we created, we can see that now there are labels for each of the categories. And so underlying is still a 0, 1, 2, 3 system, but now we've just tacked on labels to, like, a 0 means white, a 1 means black, etc. And then the last thing I'm going to do is I'm going to label our variable, like I've done in previous ones, recipient race, as race. And now if we tab it again, what we see is that the recipient race label here shows up instead of just the variable name. And so that is an overview of data cleaning. We are coming up in the hour. And so essentially what we've done, just a quick summary of everything we've done, we started our do file. We cleared all just to clear everything. We've imported our data set. In this case, it's a fake data set. We changed our directory to the folder that we're interested in. We've applied our inclusion/exclusion criteria to make the final project data set we're interested in. And now we've gone through and started cleaning our data set. And so these are just some examples of commands that we use. You can pretty much use these commands for a lot of cleaning. So this will get you quite far. Note that, for example, in this recipient race example, it was a very manual way of doing it. And there are much more efficient lines of code that you can use once you get more familiar with STATA, and you don't have to kind of type it out manually for each potential recipient race option. There are faster, more efficient ways of doing that, in that you can always learn once you understand the basics of how STATA works, how to manipulate data, how you're starting to clean everything. And I think we're going to stop here for today and see if we have any questions. All right, I can stop screen sharing. Anybody have any questions on anything we've talked about so far?
Hi, Alice. Thank you so much. I really appreciate it. I just had a question about when you were doing was it the race? You said the unknowns versus others. So we can just assume that the unknowns are others.
So in this case, what I actually did was, so if you see, so these were all the options, and I actually left the unknowns as missing. So the way I did it was I generated recipient race, and I applied values for everything but the 998, which is the unknown value. And so essentially what I've told STATA to do is leave the 998s in the new variable that I'm creating as missing value. And so in this first version, in the original variable, you'll see FCAT, there are 38,759 observations with values for this. But if you look at our new version, there's only 38,750. So those 9 are there, but they're all missing. And we don't put it as other just because technically you don't know that it's an other race, but that's a great point and a good detail to always keep in mind when you're cleaning your data. Does that make sense?
Yes, it does. Thank you. And then, sorry, let me wait for somebody else to ask another question before I ask another one.
You go ahead. I think, yeah, you can go ahead and ask, and then if anybody else has a question afterwards, they can jump in.
A codes that you use, for instance, um, hold on, let me go back to my notes. Like for the T, these codes from
It
data.
just
No,
fine, but you're cutting
those are
in and out.
coming from.
I don't know, Emily, are you able to hear?
I'm not. Do you want to send it in the chat?
Okay.
And then there was another question about changing the directory in line 12, why you would do that.
TT, you're still cutting in and out. So maybe type the question in your chat and we can answer. So point of changing the directory. So that's a great question. So we didn't get into it here, but essentially what you can do is sometimes you can save tables as output. So for example, there's a way of creating a baseline characteristic table. I'll show you in the next one of these sessions, and you can export it directly to an Excel file, and you can just save it as export it as a certain Excel file with the name that you give it, and it's going to automatically go into your folder. And so you can always just manually input the name of the folder before the file name that you want to insert. That's a way of doing it. But my way of doing it in terms of changing directory is just to make sure that everything for one project stays in one place. And so if you accidentally save something, you're not like searching for where you save the data. You know exactly where it's saving. It's being saved into this new folder for this specific project. If you export a graph or a figure, it's going to go straight into this folder. And so it's sort of just a way of keeping everything organized. Any other questions? Okay, questions. Mohammed, okay, yes, so exactly. Okay, so that's a great question. Let me open my safe desktop again. So essentially the question is for here, so race, could you have just, instead of replacing recipient male equals 0, could you just have created another variable saying that recipient female equals 1 if gender is female? You can do that, but essentially what you'd be doing is you'd be creating two separate variables, one that's 1 for female and one that's 1 for male, when what you want to do is you want to have one variable that's either 1 or 0 for female or male. And that way you can use that one variable in regressions, in your baseline characteristics tables, and we'll get into all of that next time. And so really what you want to do is you want to have it all in one variable, and instead of having two different variables that you'll have to look at simultaneously to figure out if they're male or female, it's just all in one place. I don't know if that makes sense. Okay. Any other questions? So I know it's a lot of sort of new commands, and I don't know if I explained them all correctly, but this is sort of the basics of what's going to get you through. I would say a good chunk of STATA is just knowing the generate commands, knowing the replace commands, understanding the difference between one equal sign and two equal signs, understanding how to look at your data. So with the browse window, with the summarize command, with the tab command.
I was asking a question. I think I got disconnected. I just wanted to confirm that the TX, for instance, that was the transplant dates, I
Yes.
believe. That TX came from UNOS data.
Yes. So this, yes. So this TX, that's the actual variable name. Is TX date is the transplant date, and that's UNOS data.
Gotcha. So if I were to be creating a data myself from, let's say, my institution, from my institution on Excel, so I would just come up with a name for that.
Exactly. So you can, whatever you want to name your variable, you would put it in that first row. kind of how you would like for a normal Excel file. And then I didn't get into it here, but essentially all STATA data sets are a .dta file. So that's what I opened here. But you can also import Excel data. So once you, for example, if you create your own data set in Excel, you can always import an Excel spreadsheet here. You kind of fill this out, you put in the Excel file name, you can say you want to import the first row as variable names. And so that'll automatically, whatever you put as your variable name for date, so if it's transplant date for a transplant data set, or just surgery date or operation date, whatever you call it, that's what's going to go as the variable name. And that's what you're going to use whenever you try to manipulate that specific variable.
Perfect. Thank you so much.
And similarly, if you're trying to go from a STATA file like a .dta to an Excel file, that's also super easy. And that's what I end up doing because I do my analysis in R. And so to do that, it's very similar. You just go to export and you can export it in any of those formats.
Yep. And that's because we're a big STATA group. And so we force Emily, we only provide the .dta files of our stuff, but Emily's fancier and uses R. And so she has to then go through the extra effort of importing it, exporting it, putting it into
it's just too complicated for me. Gotta get it out of there. It's my STATA knowledge.
All right. Any other questions?
Thanks so much, Alice. We appreciate you doing this, and I think everyone found it very helpful. I feel like I could maybe use STATA now.
Yes, absolutely. I'm going to throw my contact info in the chat. And if you have any other questions about what we went over today, feel free to reach out. I'm happy to answer STATA questions.
Awesome. And then we will plan to do our follow-up session to this in a few weeks and get more of Alice's wonderful expertise in making some of the figures we talked about today. So making that table 1 and making your Kaplan-Meier curves.
Yep. And sorry we didn't get to it today. I know we did all the boring stuff of just importing data and cleaning data, and all that stuff isn't as fun. But next time I promise we'll get to the more interesting stuff. So the baseline characteristics tables, regression basics, looking at some Kaplan-Meier curves, as Emily said. Yeah. So hopefully more exciting stuff to come.
No, this was